This is a smartphone, a miracle of digital engineering, right? It holds all our knowledge, connects us to the globe, and fits in our pocket. It feels like the peak of a digital world, a device built entirely from ones and zeros. But what if I told you that the soul of this machine isn't digital at all? That its most fundamental ideas weren't born in Silicon Valley, but in the minds of ancient Greek astronomers and World War II codebreakers? You think you're holding the future, but its secrets are written in the language of the mechanical past. Tonight, we uncover the story of how the ghost of analog technology haunts every device we own. Our journey begins not in a clean room, but in the murky depths of the Aegean Sea. The year is 1901. Sponge divers discover the wreck of an ancient Roman ship off the coast of Antikythera. Amidst the artifacts, they find a corroded lump of bronze, a shoebox-sized mystery. For decades, no one knew what it was, but as modern imaging let scientists peer inside, they uncovered a breathtaking complexity. A clockwork of over 30 interlocking bronze gears. A device so precise, nothing like it would be seen for over 1,000 years. This was the Antikythera mechanism, now understood to be the world's first known analog computer. Built around the 2nd century BC, you couldn't check your email on it. Its purpose was far grander. Turn a hand crank and its gears would model the cosmos. Pointers would glide across its face, predicting the position of the sun, the moon, and the known planets. Could even track the 4-year cycle of the Olympic Games. Think about the genius of this. It was a machine that used continuous physical motion, the rotation of gears, to solve incredibly complex math. It didn't just compute numbers. It simulated reality. It was an analog device. Data wasn't ones and zeros. It was the angle of a gear, the position of a pointer. That was information. While the Antikythera mechanism was an astonishing anomaly, its spirit was shared by another ancient device, the astrolabe. Used for centuries, it was the original smartphone, a handheld astronomical calculator for telling time, finding your latitude, and identifying stars. A portable, problem-solving machine. Both devices embody the same idea, using the physical world to compute your place in it. This concept of a pocket-sized calculator for reality is the earliest known ancestor of your phone's GPS and clock. The technology was lost, but the idea, it never truly went away. But this idea of mechanical calculation didn't disappear. It just went quiet for a while, its gears buried by the sands of time. It would re-emerge centuries later, not to chart the stars, but to weave patterns and, eventually, to break codes. The next step wasn't about simulating the world as it was, but about telling a machine what to do. The next chapter takes us to a surprisingly different place. A textile factory in 19th century France. For centuries, weaving complex patterns was incredibly slow work. Enter Joseph-Marie Jacquard. In 1801, he demonstrated an invention that would change everything. The Jacquard loom. It automated the entire process. And the genius was its control mechanism. A series of connected cards with holes punched into them. Rods passed through the holes, lifting specific threads. No hole, no lift. It was a simple binary system, hole or no hole. On or off. By stringing these cards together, Jacquard could create a program, a set of repeatable instructions for weaving any design. This was a watershed moment. The idea of using a readable program to control a machine inspired the English mathematician Charles Babbage for his never-built analytical engine. His colleague Ada Lovelace realized that if the machine could manipulate numbers, it could manipulate anything: music, letters, symbols, presaging the very concept of modern software. This concept reached a brutal, high-stakes climax during World War II. The German military communicated using the Enigma machine, a devilishly complex electromechanical device that used rotating scramblers to create a cipher that changed with every single keystroke. For years, it was considered unbreakable. Breaking Enigma fell to a team of brilliant minds at Bletchley Park, led by the legendary Alan Turing. They developed an electromechanical device designed for one purpose: to find the daily Enigma settings. They called it the bomb. The bomb wasn't a computer like we know it. It was a special-purpose logic machine. It churned through thousands of possible Enigma configurations at high speed, looking for a single logical contradiction. The bombs were enormous, filled with dozens of spinning drums that simulated the Enigma rotors. They were noisy, clattering behemoths, the sound of pure mechanical logic searching for a single truth. From the jacquard loom to the bomb, the principle had evolved. A simple binary instruction, whole or no hole, had become the foundation for automated, high-speed logical machines. The stage was set for the next revolution. These machines, born from war and industry, proved that complex logic could be automated. But they were enormous, clunky, and fundamentally mechanical. The next leap wouldn't be about making the gears more complex, but about getting rid of them altogether. It was time for the digital dawn. But the transition had its own unsung analog heroes. During World War II, a German engineer named Helmut Holzer designed the world's first fully electronic analog computer to guide the V-2 rocket. Built in 1941, it used vacuum tubes to perform calculus in real time, a direct ancestor of the control systems in every modern plane and spacecraft. Holzer's machine showed the power of using electricity to solve problems continuously. But even as electronic analog computers were hitting their peak in the 50s and 60s, their time was coming to an end. The invention of the transistor and later the integrated circuit changed everything. Digital computing operating on ones and zeros was faster, more accurate, and data could be copied infinitely without loss. By the 1970s, with the rise of the microprocessor, digital had decisively won. The age of gears and varying voltages seemed to be over. But here is the crucial twist in our story. Analog didn't die. It didn't even fade away. It simply found a new and arguably more important role. It became the essential bridge between the messy, continuous reality of our world and the clean, orderly world of digital processing. Digital computers are powerful, but they are fundamentally deaf and blind. The world we live in is not made of ones and zeros. It is, in its very essence, analog. For a digital device to do anything useful, it needs a translator, an interface to the real world. That interface is pure analog technology. This brings us back to the smartphone in your pocket. You think of it as a digital device, but it's a hybrid, a masterful fusion of two different worlds. Every single way your phone interacts with reality is an analog process. Let's start with your voice. When you speak, you create sound waves, continuous variations in air pressure. The microphone's tiny diaphragm vibrates, and that vibration is converted into a continuously varying electrical voltage. An analog signal. A perfect electrical copy of your voice. This signal is weak and noisy, so before it can become digital, analog circuits amplify it and filter out noise. Only then is this clean analog signal passed to the unsung hero of your phone, the analog-to-digital converter, or ADC. The ADC translates the language of the physical world into the language of the computer, sampling the signal thousands of times a second and assigning a digital value to each point. This same process happens everywhere. Your phone's camera? Its sensor generates a continuous electrical charge based on the light it sees. This massive array of analog signals is then converted into the digital pixels that form your photos. The GPS, our modern-day astrolabe, listens for faint, continuous radio waves from space. The phone's antenna is a sophisticated analog system that captures and cleans these signals before an ADC can digitize them. Every sensor, for motion, direction, air pressure, works by translating a physical quantity into an analog electrical signal. Without these sophisticated analog front ends, your phone would be a useless brick. The digital brain inside is incredibly powerful, but its intelligence is entirely dependent on the information it gets from a hidden world of analog circuits. It's incredible to think about how many layers of history are stacked inside this one device. Now, let me know in the comments, what other piece of modern tech do you think has a secret analog past? And if you enjoy these deep dives into the hidden history of technology, subscribe now and join us next time as we uncover more forgotten technologies that shaped our digital lives. So, let's trace the line one last time. The fundamental purpose of the astrolabe lives on in the analog circuits of your GPS. The revolutionary principle of the Jacquard loom, storing instructions to control a machine, is the direct ancestor of every app on your phone. The high-speed logic of the World War II codebreakers laid the groundwork for the processor in your pocket. Your smartphone is not a departure from this history. It is the stunning culmination of it. It proves that digital and analog are not opposing forces, but complementary ones. Digital provides the logic, but analog provides the connection to reality. So the next time you pick up your phone, take a moment to appreciate its hidden lineage. You're not just holding the future, you're holding a museum of human innovation. The soul of this new machine is ancient,